Welcome to Mystery Beyond Reason, where we dive deep into the unknown. Space, the final frontier. Beyond the shimmering lights of our night sky lies a universe full of mysteries that even the greatest minds of our time struggle to understand. How did it all begin? Where does it end? Are we truly alone? Or could other civilizations be scattered across the stars, hidden just beyond our reach? As we journey through the depths of the cosmos, we'll explore 25 of the most mind-bending space mysteries that continue to defy explanation. Some of these enigmas hint at forces beyond our comprehension, while others challenge the very fabric of reality as we know it. From the nature of black holes to the search for extraterrestrial life, these cosmic puzzles push the boundaries of human knowledge. But be warned, the deeper you look into space, the more the universe seems to look back at you, raising questions that could change everything we thought we knew. Are you ready to unlock the secrets of the cosmos? Before we begin, don't forget to subscribe to Mystery Beyond Reason and hit the notification bell so you never miss out on our latest explorations into the unknown. The first mystery on our list strikes at the core of one of humanity's greatest questions. Are we alone in the universe? The Fermi paradox presents a chilling conundrum. Given the sheer number of stars in our galaxy, over 100 billion, and the countless Earth-like planets potentially orbiting them, we should have made contact with intelligent extraterrestrial civilizations by now. So, where are they? Pause for a moment and consider. If the universe is teeming with life, as the numbers suggest, why haven't we heard even a whisper? Could it be that other civilizations are purposefully avoiding us, hiding in the vastness of space? Or worse, have they already come and gone, victims of some cosmic disaster? This mystery takes us deeper into the unknown than most are prepared for. One explanation offered by scientists is that advanced civilizations are simply too far away for us to detect. The distances between stars are vast. So vast that it could take hundreds or even thousands of years for signals to reach us, even if they were sent deliberately. Perhaps we've simply missed the signals, or they've yet to reach our corner of the galaxy. But others suggest a darker possibility, the Great Filter hypothesis. This theory suggests that there's some catastrophic event or universal barrier that prevents civilizations from advancing to the point of interstellar communication. If that's the case, could humanity be approaching that filter now? What if we're not alone at all, but instead part of a cosmic zoo where more advanced species watch us, silently observing our progress or our downfall? Or worse, what if something out there doesn't want us to know they exist? Could we be the only survivors of a galactic-scale extinction event? Or are the answers out there, hiding just beyond our ability to detect them? Now, let's turn our attention to something even more elusive: dark matter. You've heard the phrase before, but do you truly understand its implications? Imagine looking up at the stars, knowing that everything you see, every planet, star, and galaxy, makes up only a small fraction of the universe's true mass. The rest, it's invisible. This is dark matter, and it makes up 27% of the universe, but we can't see it, touch it, or interact with it. We only know it exists because of its gravitational pull on the visible universe. Think about it. If dark matter were suddenly to disappear, galaxies would fly apart like marbles scattered across a floor, unable to hold themselves together. But what exactly is it? Here's where the mystery deepens. Scientists have long suspected that dark matter consists of some unknown type of particle, perhaps WIMPs, weakly interacting massive particles, or maybe axions, another exotic candidate. But despite massive detectors buried underground, searching for the faintest interaction with these particles, we've found nothing. Imagine standing in a pitch-black room where everything moves around you, yet you can't see or touch any of it. That's the situation scientists face when studying dark matter. Could dark matter be something we haven't even considered? Something beyond the realm of current physics? Some even suggest that dark matter might be composed of primordial black holes left over from the early universe. Or what if dark matter isn't matter at all, but rather a manifestation of gravity itself, behaving in ways we don't yet understand? The truth about dark matter could reshape our understanding of the universe? Could the key to dark matter lie in a deeper theory of reality? Or are we looking in the wrong places entirely, chasing a ghost in the cosmic machine? Stay with us as we continue unraveling the most profound mysteries of the universe. If dark matter holds the universe together, then dark energy is the force pushing it apart. And it's doing so at an accelerating pace. Discovered in the late 1990s, dark energy accounts for nearly 70% of the universe. But what is it? And why is the universe expanding faster and faster instead of slowing down? The discovery of dark energy changed everything we thought we knew about the cosmos. Imagine standing on a beach, watching the tide go out, but instead of slowing down and returning, the water speeds away faster and faster, vanishing into the horizon. That's what dark energy is doing to galaxies. It's stretching the very fabric of space-time, pulling galaxies further apart at a rate no one saw coming. Dark energy is the mysterious force that counteracts gravity and is believed to drive the expansion of the universe. But it's more than that. Some physicists propose that dark energy could be a property of vacuum energy, the energy of empty space itself. Others suggest it could be a new fundamental force, something that doesn't interact with matter as we know it. Another possibility is that dark energy might be the result of changes in the very structure of space and time on a cosmic scale. As space expands, new dark energy appears, accelerating the process even further. Could dark energy one day tear the universe apart in what scientists call the Big Rip? Imagine a future where galaxies, stars, and eventually even atoms are torn to pieces, leaving a cold, desolate void. The fate of the universe might very well rest in our understanding or misunderstanding of dark energy. What could we uncover about the true nature of the cosmos if we unlock its secrets? Black holes. Just saying the words evokes a sense of awe, fear, and mystery. These cosmic monsters defy the rules of physics as we understand them. A black hole is a region of space where gravity is so strong that not even light can escape. But there's so much more to them than that. What happens when you fall into a black hole? Does time stop? Do the laws of physics break down? And perhaps the most tantalizing question of all, could black holes be portals to other universes? Imagine being on the edge of a black hole's event horizon, the point of no return. Time slows to a crawl. To an outside observer, you would appear to freeze in place, forever trapped on the edge. But for you, time continues normally, until you are stretched into infinity by the black hole's gravity. It's almost unimaginable, yet it's happening right now at the center of countless galaxies. At the heart of a black hole lies a singularity, a point where matter is crushed to infinite density, and the known laws of physics no longer apply. But the event horizon is where the real mystery lies. Once something crosses it, there's no coming back. What happens beyond this boundary remains unknown. Do black holes lead to other dimensions, as some physicists suggest? Could they be connected by wormholes, allowing travel across vast distances or even to parallel universes? Stephen Hawking once proposed that black holes might not be entirely black. They could emit faint radiation, now known as Hawking radiation, eventually causing them to evaporate over time. But here's the kicker. If information is destroyed in a black hole, what does that say about the universe's fundamental principles? In physics, information is never supposed to be lost, but black holes might challenge this very idea. Is it possible that the universe itself began as a singularity, much like a black hole, only in reverse? Could black holes hold the key to understanding the origin and ultimate fate of the universe? Some even speculate that entire universes could exist inside black holes. We've only just begun to scratch the surface of these cosmic beasts. What secrets do they still hold, waiting to be unlocked? Is this universe the only one? Or are we just one small part of an endless sea of universes, each with its own rules, its own physics, and its own history? This is the question posed by the multiverse theory, and it's one of the most mind-blowing concepts in modern physics. What if there's another universe where you made different choices, where stars are made of different elements, or where life as we know it evolved in completely different forms? The multiverse theory suggests that all of this and more is possible. But it's not just science fiction. Theoretical physics provides real mathematical support for the idea that our universe could be just one of many. The multiverse theory arises from several different areas of physics, one of the most prominent being cosmic inflation. The idea here is that shortly after the Big Bang, the universe underwent a period of rapid expansion, creating bubble-like regions of space-time. Each of these bubbles could be a separate universe with its own set of physical laws. Another version of the multiverse comes from quantum mechanics. According to this theory, every time a quantum event occurs with multiple possible outcomes, the universe splits into different realities, one for each outcome. This creates a constantly branching multiverse, where every possible version of history exists somewhere. Then there's the idea of string theory, which suggests that extra dimensions beyond the three we experience could give rise to multiple universes. If string theory is correct, our universe might be one of many, each with different numbers of dimensions or fundamental forces. If the multiverse is real, it raises profound questions. Could there be other versions of us, living different lives in parallel realities? Could we ever communicate with or travel to these other universes? And what would it mean for our understanding of reality itself? The multiverse might just be the key to solving some of the greatest mysteries of physics. But for now, it remains one of the most mind-bending possibilities ever proposed. At the moment of the Big Bang, matter and antimatter should have been created in equal amounts. For every proton, there should have been an antiproton. For every electron, an anti-electron. And yet, when we look around the universe today, we find almost no antimatter. Everything we see is made of regular matter. So, what happened to all the antimatter? Imagine a universe where antimatter and matter were balanced, where entire galaxies were made of antimatter and their interactions with regular matter produced unimaginable amounts of energy. But our universe didn't turn out that way. Instead, antimatter is nearly non-existent, and scientists have been scratching their heads for decades trying to figure out why. One theory suggests that there was a tiny imbalance in the amounts of matter and antimatter produced during the early moments of the universe, an asymmetry so small that for every billion particles of antimatter, there was one extra particle of matter. Over time, this tiny excess of matter became everything we see today. But that explanation still leaves many questions unanswered. Why was there an imbalance in the first place? What process caused matter to dominate the universe, leaving antimatter nearly extinct? Some physicists believe that this mystery might be linked to CP violation, a phenomenon where particles and their antiparticles behave slightly differently under certain conditions. Experiments have observed this violation in certain particles, but not enough to explain the missing antimatter. Others propose more exotic solutions, such as sterile neutrinos, particles that interact only with gravity and might have played a role in the universe's matter-antimatter asymmetry. Could there be regions of the universe where antimatter still exists, waiting to be discovered? Or is the antimatter problem connected to something even stranger, a breakdown in the symmetry of nature itself? Solving this mystery could unlock secrets about the universe's earliest moments. But for now, the missing antimatter remains a profound cosmic puzzle. In 1977, something extraordinary happened. A signal was detected from space that was unlike anything ever recorded before. It was so strong, so distinct, and so unexpected that it left scientists at a loss. Astronomer Jerry Ehman, who discovered the signal, was so amazed that he circled it on the printout and wrote one word beside it: wow. This is the story of the WOW signal, one of the most tantalizing clues in the search for extraterrestrial life. The WOW signal was a 72-second burst of radio waves coming from the direction of the constellation Sagittarius. It was detected by the Big Ear Radio Observatory, which was scanning the skies for possible extraterrestrial signals. But here's the catch. Despite numerous attempts to detect the signal again, it has never been observed a second time. Was this a one-time message from an alien civilization, or was it something else entirely? The WOW signal had all the hallmarks of a transmission from deep space. It didn't match any known natural sources like pulsars or quasars, and its strength suggested it came from a distant point far beyond our solar system. But the real mystery is why it has never repeated. If it were an alien transmission, wouldn't we expect to hear it again? Some scientists have proposed that the signal could have been a reflection of human-made radio interference, but no conclusive evidence has been found to support this. Others speculate that the WOW signal could have been a message from an advanced civilization that we just happened to catch by sheer luck, a brief window into a moment of communication from across the galaxy. If that's the case, how much more might we be missing? Could signals like this be passing by all the time, too fleeting for us to detect? What if the WOW signal wasn't a random burst, but a deliberate message? And if so, what were they trying to tell us? Was it a hello, or could it have been a warning from a distant civilization? The WOW signal remains one of the greatest unsolved mysteries in the search for extraterrestrial life. Could it be the key to proving that we are not alone? In 2017, an object entered our solar system that was unlike anything we had ever seen before. It came from another star system, moving at an incredible speed and on a path that didn't match any known comet or asteroid. This was Oumuamua, the first interstellar object ever detected passing through our solar system. But what exactly was it? Oumuamua was unlike any object astronomers had ever encountered. It was long and thin, shaped more like a cigar or a needle than a typical space rock. And as it passed by the sun, it accelerated in a way that didn't fit the behavior of a comet or asteroid. Was Oumuamua an alien probe sent to explore our solar system? Or was it some natural object from a distant star, unlike anything we've seen before? The name Oumuamua means scout in Hawaiian, reflecting its status as the first known visitor from another star system. Initially, scientists thought it might be a comet, but Oumuamua didn't have the typical tail of gas and dust that comets usually display when they approach the sun. Instead, it moved through the solar system with a strange, tumbling motion, accelerating as it passed by. Some have suggested that the acceleration was caused by outgassing, the release of gas from the object's surface, but no gas was detected. Others have proposed that it could be a fragment of a larger body that was ejected from its home star system during some violent event, such as a planetary collision. But the most intriguing possibility is that Oumuamua could be an alien artifact, perhaps a probe or a piece of advanced technology sent by another civilization. Harvard astronomer Avi Loeb famously suggested that Oumuamua's unusual shape and acceleration could be the result of a light sail, a type of propulsion system powered by starlight. Could we have just missed our first contact with extraterrestrial technology? As Oumuamua continues its journey out of the solar system, it leaves us with more questions than answers. Could it be a natural object unlike any we've seen before, or is it evidence of advanced extraterrestrial engineering? Will we ever encounter another visitor from the stars, or was Oumuamua a once-in-a-lifetime event? The mystery of Oumuamua challenges our understanding of the cosmos and leaves the door wide open to speculation. Imagine a star that behaves so strangely that some scientists think it could be surrounded by an alien megastructure. That's exactly what happened in 2015 when astronomer Tabitha Boyajian and her team discovered a star that didn't behave like any other. The star, known as KIC 8462-852, or more famously, Tabby's star, exhibited unpredictable and extreme dimming events, unlike anything seen before. Could an advanced alien civilization be building something around Tabby's star, like a Dyson sphere, to harness its energy? Or is there another explanation for this bizarre behavior? The strange dimming of Tabby's star captured the imagination of astronomers and the public alike, leading to some of the wildest speculation in recent years. A Dyson sphere is a hypothetical structure built around a star to capture its energy, providing an advanced civilization with nearly unlimited power. When Tabby's star started to dim by up to 22%, some wondered if we might be witnessing the construction of such a megastructure. But before we jump to conclusions, let's explore other possibilities. Tabby's star could be surrounded by a cloud of dust or comets, which might cause the irregular dimming. However, observations have ruled out many of the more mundane explanations. The dimming is too erratic to be caused by a simple dust cloud, and the sheer scale of the dimming events is unlike anything we've seen in other stars. This leaves the door open to more exotic theories. While the alien megastructure hypothesis has yet to be proven, Tabby's star remains one of the strangest objects in the cosmos. Could we be witnessing the work of an advanced civilization? Or is there an unknown natural process at play, waiting to be discovered? Tabby's star continues to puzzle astronomers, leaving us with tantalizing questions about what's really happening in the depths of space. Time. It governs everything we do, yet we barely understand it. We experience time as a river flowing in one direction, from past to future. But why? The laws of physics don't require time to have a direction. In theory, time could flow backward just as easily as it flows forward. So why does time seem to only move in one direction? Imagine if time flowed backward. What would that look like? Would the universe unexpand? Galaxies collapsing back into a singularity? Would memories unwrite themselves, events happening in reverse, leading us to a past that never stops looping? The concept of time's arrow, the idea that time has a specific direction, is one of the most profound mysteries in physics. One explanation for the one-way nature of time is entropy. The second law of thermodynamics states that entropy, or disorder, always increases over time. This creates a natural direction for time. As the universe becomes more disordered, time marches forward. But does that really explain everything? Could there be deeper forces at play that govern the flow of time? Some physicists speculate that time itself might be an emergent property, a result of more fundamental processes that we don't yet understand. Another mystery is the connection between time and gravity. Einstein's theory of general relativity tells us that gravity can warp time, slowing it down near massive objects like black holes. But what does that mean for the nature of time itself? Could there be regions of the universe where time behaves differently or even flows in the opposite direction? If time is a river, could we one day learn to reverse its flow? What if the one-way arrow of time is not a fundamental feature of the universe, but something that can be bent or broken under the right conditions? The mysteries of time challenge our understanding of reality itself. Could we ever unlock the secret to controlling time, or will we forever be bound by its relentless march forward? The universe is expanding. That's not just a theory, it's a fact. Ever since Edwin Hubble first observed the redshift of galaxies in the 1920s, we've known that the universe is getting larger. But here's the mystery. We don't know exactly how fast this expansion is happening. And the more we try to measure it, the more contradictions we find. Imagine for a moment that you're looking at a balloon being blown up. The galaxies are like dots on the surface of that balloon, moving further apart as the universe expands. But how fast is the balloon inflating? That's what scientists have been trying to figure out for decades. The rate of this expansion is known as the Hubble constant, and it's causing some real headaches for cosmologists. There are two main ways to measure the Hubble constant. One method uses the cosmic microwave background radiation, which is the afterglow of the Big Bang, to calculate how fast the universe was expanding in its earliest stages. The other method uses supernovae and Cepheid variable stars to measure the expansion rate in the local universe today. But here's the problem. These two methods give different results. The cosmic microwave background suggests that the universe is expanding at about 67 kilometers per second per megaparsec, but measurements of nearby galaxies give a faster rate, around 74 kilometers per second per megaparsec. This discrepancy has been dubbed the Hubble tension, and no one knows why the two numbers don't match. Could there be something we're missing about the early universe? Or is there a deeper, fundamental issue with how we understand the cosmos? Could solving the Hubble tension reveal something groundbreaking about the universe? Some scientists speculate that it could point to new physics, perhaps even a sign of an unknown force or particle influencing the expansion of the universe. Is the answer waiting to be discovered, or does this mystery signal that our understanding of the universe is fundamentally flawed? Our galaxy, the Milky Way, is not standing still. In fact, it's hurtling through space at an incredible speed of 2 million kilometers per hour. But here's the real question. Where is it going, and what's pulling it? The answer lies in one of the most puzzling phenomena in the universe: the Great Attractor. Imagine being pulled towards something enormous, something you can't see or touch, but you know it's there. You feel its gravitational pull, but it lies hidden behind a vast curtain of stars and dust. This is what astronomers are grappling with as they study the Great Attractor, a gravitational anomaly in deep space that seems to be pulling our entire galactic neighborhood toward it at mind-boggling speeds. The Great Attractor is located about 150 to 250 million light-years away in a region known as the Zone of Avoidance. This area is obscured by the Milky Way's bright stars and dense dust, making it nearly impossible to observe directly. Despite this, scientists know the Great Attractor exists because of its gravitational influence on surrounding galaxies. It's pulling not just our galaxy, but millions of others toward it. But what is the Great Attractor? Some theories suggest it could be a massive cluster of galaxies, while others speculate that it's an enormous concentration of dark matter, a substance that we can't see, but that makes up most of the universe's mass. Whatever it is, it's shaping the large-scale structure of the universe, pulling galaxies across vast distances toward a hidden cosmic hub. What lies behind the Zone of Avoidance? Could the Great Attractor be an immense supercluster of galaxies? Or is there something even stranger, an undiscovered feature of the universe we've yet to comprehend? As telescopes get more powerful and our understanding of dark matter deepens, we may soon unveil the true identity of this cosmic enigma. But until then, the Great Attractor remains one of the most mysterious forces in the universe, pulling us closer with each passing second. In the 1960s, two astronomers stumbled upon a discovery that would forever change our understanding of the universe. They found a faint glow that seemed to come from every direction in space. This glow, known as the cosmic microwave background, CMB, is the oldest light in the universe, an echo of the Big Bang that gave birth to everything we know. Imagine looking out into space and seeing not just stars and galaxies, but the remnants of the very moment when the universe was born. That's what the cosmic microwave background represents. It's a snapshot of the universe as it was just 380,000 years after the Big Bang, when the first light was able to travel freely through space. But this cosmic relic holds more mysteries than answers. The cosmic microwave background is incredibly uniform, with only tiny variations in temperature, about 1 part in 100,000. These fluctuations are the seeds that eventually grew into galaxies and clusters of galaxies. But within this uniformity lies a puzzle: the cold spot. The region of the CMB is significantly colder than its surroundings, and no one knows why. Some theories suggest it could be the result of a massive void in space, while others propose that it might be evidence of something far more exotic, like a collision with another universe. The CMB also provides clues about the shape and geometry of the universe. By studying its patterns, scientists have determined that the universe is remarkably flat, meaning that if you traveled in a straight line, you'd never come back to where you started. But does this flatness hold true on cosmic scales beyond what we can observe? Or could the universe be curved in ways we can't yet detect? Is the cosmic microwave background hiding more secrets about the early universe? Could the cold spot be a remnant of a previous cosmic collision, or is it a signal from beyond our known universe? As we continue to map the CMB with greater precision, we may uncover answers that challenge everything we thought we knew about the origins of the cosmos. When a massive star dies, it doesn't go quietly. After it explodes in a supernova, the core collapses into one of the strangest objects in the universe, a neutron star. These are the densest objects we know of, with a mass greater than that of the Sun, packed into a sphere just 20 kilometers across. But the mysteries of neutron stars go far beyond their density. Imagine something so dense that a single teaspoon of its material would weigh more than 1 billion tons. That's the reality of a neutron star. These cosmic behemoths are created when the core of a supermassive star is crushed to the point where protons and electrons combine to form neutrons. But even though we know how they form, neutron stars are still shrouded in mystery. Neutron stars spin at incredible speeds, with some rotating hundreds of times per second. These are known as pulsars, and they emit beams of radiation that sweep across the sky like cosmic lighthouses. But the extreme conditions inside a neutron star are beyond anything we can replicate on Earth. The surface gravity is about 200 billion times stronger than Earth's, and the magnetic fields are trillions of times more intense. One of the most intriguing questions about neutron stars is what happens at their core. Some theories suggest that the pressure is so intense that neutrons themselves break down, forming an even more exotic state of matter known as quark matter. Could this be the key to understanding the true nature of matter at the smallest scales? And then there are magnetars, a type of neutron star with magnetic fields so powerful that they could distort atoms and even disrupt electronic devices from thousands of kilometers away. What are the limits of a neutron star? Could they collapse even further into black holes? Or do they hold secrets about the fundamental forces of nature? The study of neutron stars is still in its infancy, and each discovery brings us closer to unlocking the mysteries of matter under the most extreme conditions imaginable. Planets are supposed to orbit stars. That's the natural order, right? But not all planets play by the rules. Some wander through the galaxy alone, without a parent star to guide them. These are rogue planets, and they're some of the most mysterious objects in the universe. Imagine a world without a sun, a planet drifting through the cold darkness of space, completely isolated from the light and warmth of a star. These rogue planets are thought to be more common than we ever imagined. There could be billions of them in our galaxy alone. But how do they form, and what happens to them as they drift through the void? Rogue planets are believed to form in the same way as regular planets, around stars. But something goes wrong. Perhaps they're ejected from their parent star system by a close encounter with another planet. Or maybe they form in isolation from the beginning, never having a star to call home. These planets are incredibly difficult to detect because they don't emit light like stars, and they don't reflect enough light for us to see them directly. Despite this, astronomers have found evidence of rogue planets through a phenomenon called gravitational microlensing. When a rogue planet passes in front of a distant star, its gravity can bend the light from that star, creating a brief but detectable event. Some rogue planets may even have thick atmospheres or subsurface oceans that could potentially support life, even without a star to provide heat. Could there be rogue planets drifting through our solar system, unseen and undetected? What kinds of environments might exist on these lonely worlds, and could life thrive in the darkness? The discovery of rogue planets challenges our understanding of what a habitable world might look like, and the search for them is only just beginning. In 2007, astronomers detected something extraordinary. Brief, intense bursts of radio waves from deep space. These events, known as fast radio bursts, FRBS, last only milliseconds, but release more energy than the sun does in an entire day. And here's the kicker, we still don't know what's causing them. Imagine sitting at your radio telescope, scanning the sky, when suddenly you detect a signal, a flash of energy so powerful it defies explanation. But just as quickly as it appeared, it's gone. leaving nothing but questions in its wake. That's what happened with the first FRB, and since then, dozens more have been detected. Are they natural phenomena, or could they be signals from advanced civilizations trying to communicate with us? FRBs are mysterious for several reasons. First, they're incredibly bright and brief, making them difficult to study. Second, they seem to come from all over the sky, from distant galaxies millions or even billions of light years away. Most FRBs are one-off events, but a few have been observed to repeat, adding another layer of complexity to the mystery. Some scientists believe that FRBs could be the result of neutron star mergers, black hole collisions, or magnetars releasing massive amounts of energy. Others propose more exotic explanations, such as advanced alien civilizations using powerful beams of energy to propel spacecraft across the galaxy. Could we be witnessing the first signs of an intergalactic communication network? The more FRBs we detect, the more questions we have. Are they natural, or could they be artificial? As new telescopes come online and our ability to study these enigmatic signals improves, we may finally uncover the truth behind these mysterious bursts of energy. But until then, the origin of FRBs remains one of the most tantalizing, unsolved mysteries in modern astronomy. Our solar system is far larger than just the planets. Beyond Neptune lies a vast region filled with icy bodies and dwarf planets. This is the Kuiper belt. And even further out, at the very edge of the sun's gravitational influence, lies the Oort cloud, a shell of icy objects that may hold the key to understanding the formation of our solar system. Imagine a distant region of space where the sun is just a faint point of light, barely illuminating the frozen remnants of our solar system's birth. The Kuiper belt and Oort cloud are like the attic of the solar system, filled with ancient relics that have remained largely untouched for billions of years. But what secrets do they hold, and what mysteries might we uncover as we explore these distant regions? The Kuiper belt is home to many dwarf planets, including Pluto and Eris, as well as countless smaller objects made mostly of ice and rock. These objects are remnants from the early solar system left over from the formation of the planets. But the real mystery lies even further out, in the Oort cloud, a vast spherical shell of icy bodies that may extend up to a light year from the sun. The Oort cloud is thought to be the source of long-period comets, those that take hundreds or even thousands of years to complete an orbit around the sun. But here's the catch: we've never actually seen the Oort cloud. Its objects are too small and too far away to detect directly. So how do we know it exists? The answer lies in the behavior of long-period comets, which seem to come from all directions, suggesting they originate in a distant, spherical region surrounding the solar system. What lies beyond the Oort cloud? Could there be even more distant objects waiting to be discovered? Or is the Oort cloud the final frontier of our solar system? As we continue to explore the Kuiper belt and beyond, we may find clues to the origins of our solar system, or perhaps even the first signs of a distant planet lurking in the darkness. For centuries, we thought our solar system had 9 planets. Then, in 2006, Pluto was reclassified as a dwarf planet, leaving us with just 8. But recent evidence suggests there might still be a 9th planet out there, an enormous hidden world far beyond the orbit of Neptune. Imagine a planet 10 times the mass of Earth, so far away that it takes 10,000 to 20,000 years to complete a single orbit around the Sun. This is Planet 9, a hypothetical world that could be lurking in the outer reaches of the solar system, beyond even the Kuiper belt. Could it be real? And if so, why haven't we found it yet? The idea of Planet 9 came about when astronomers noticed something strange about the orbits of several distant objects in the Kuiper belt. These objects seemed to be clustered together in a way that couldn't be explained by the gravitational influence of the known planets. The best explanation? A massive, unseen planet far beyond Neptune, whose gravity is affecting the orbits of these distant objects. But finding Planet 9 is no easy task. It's so far away and so dim that even our most powerful telescopes might struggle to detect it. And its orbit is so long that it could take centuries or even millennia to complete one trip around the Sun. Still, the evidence for its existence is compelling, and many astronomers believe it's only a matter of time before we find this hidden world. Could Planet 9 be the last major planet in our solar system, or is there something even stranger affecting the orbits of these distant objects? As telescopes become more advanced and our understanding of the outer solar system grows, we may finally catch a glimpse of this elusive world. Until then, Planet 9 remains one of the greatest mysteries of our cosmic neighborhood. At the center of our galaxy lies a monster, a supermassive black hole known as Sagittarius A. With a mass of over 4 million suns, this black hole dominates the heart of the Milky Way, shaping the orbits of nearby stars and influencing the structure of the entire galaxy. Imagine a region of space so extreme that time itself slows to a crawl, where gravity is so strong that not even light can escape. That's what lies at the center of our galaxy. But Sagittarius A is more than just a black hole. It's a window into the most extreme conditions in the universe, and studying it could unlock some of the deepest mysteries of space and time. Sagittarius A is surrounded by a chaotic environment, with stars whipping around it at incredible speeds. One of these stars, known as S2, has been observed making a complete orbit around the black hole, providing astronomers with a unique opportunity to study the effects of extreme gravity. As the star approaches the black hole, its speed increases dramatically, reaching up to 3% of the speed of light. But Sagittarius A isn't just sitting quietly at the center of the galaxy. Occasionally, it emits powerful flares of energy as matter from nearby stars is pulled into its event horizon. These flares give us glimpses into the violent processes happening near the black hole's edge, but they also raise new questions. Why does Sagittarius A star flare up at seemingly random intervals? Could there be hidden objects, like neutron stars or other black holes, orbiting near the galactic center and influencing its behavior? Could Sagittarius A hold the key to understanding black holes and the role they play in the evolution of galaxies? As new telescopes like the Event Horizon Telescope continue to study the galactic center, we may soon get our first detailed images of the event horizon itself. But what we find could change our understanding of the universe's most extreme objects forever. We live in a universe that stretches out in all directions, but what is its true shape? Is the universe infinite, or does it have an edge? And if it does have an edge, what lies beyond? These questions have puzzled cosmologists for centuries, and the answers could reshape our understanding of reality itself. Imagine traveling in a straight line through space, never turning back, never stopping. Would you eventually return to the point where you started, or would you keep going forever into an infinite expanse? The shape of the universe determines whether it's finite or infinite, and understanding it could unlock some of the deepest mysteries of cosmology. The shape of the universe is determined by its curvature. If the universe has positive curvature, it would be shaped like a sphere, and traveling in a straight line would eventually bring you back to your starting point. If it has negative curvature, it would be shaped like a saddle, and space would continue to expand forever. A flat universe, which is what current observations suggest, is the middle ground, where space extends infinitely in all directions without curving back on itself. The cosmic microwave background radiation provides some of the best evidence for a flat universe, but the true shape of the cosmos might be more complicated. Some theories suggest that the universe could be finite but unbounded, like the surface of a balloon. In this model, you could travel in a straight line forever without reaching an edge, but space would still have a finite volume. Other theories propose that the universe might have extra dimensions hidden from our view that could drastically alter its geometry. Is the universe truly infinite, or could there be hidden boundaries we haven't yet detected? Could we one day discover that our universe is just one bubble in a multiverse of countless other universes, each with its own shape and structure? The true nature of the cosmos remains one of the greatest unanswered questions in science, and solving it could change our understanding of everything. When you look at the night sky, you see stars scattered across the heavens. But on a cosmic scale, the universe isn't random. It's organized into an immense, intricate structure known as the cosmic web. This web is made up of galaxies, galaxy clusters, and filaments of dark matter, all connected in a vast, interconnected network that stretches across the universe. Imagine a spider web, but on a scale so vast that it spans billions of light years. This is the cosmic web, the underlying structure of the universe that holds everything together. But how did this web form, and what role does dark matter play in its construction? As we map the universe in greater detail, we're beginning to uncover patterns that challenge our understanding of how the cosmos came to be. The cosmic web is made up of filaments, long, thin strands of galaxies and dark matter that stretch across space. These filaments intersect at nodes, where massive galaxy clusters reside, and between them are vast voids, empty regions of space with very few galaxies. The cosmic web is thought to have formed through the process of gravitational collapse, as dark matter pulled galaxies together into dense filaments and clusters. But mapping the cosmic web is no easy task. Much of the matter in the universe is dark matter, which doesn't emit or reflect light, making it invisible to telescopes. Instead, astronomers use the gravitational effects of dark matter to trace the structure of the web. By observing how galaxies move and how light is bent by gravity, we can map out the distribution of dark matter and reveal the true shape of the cosmic web. What secrets does the cosmic web hold about the origins of the universe? Could the patterns we see in the distribution of galaxies provide clues to the nature of dark matter and dark energy? As we continue to study this vast structure, we may uncover new insights into the forces that shape the universe, and perhaps even find hints of other universes hidden within the web. We've all heard of black holes, regions of space where gravity is so strong that nothing, not even light, can escape. But what if there's an opposite to a black hole? A region of space that, instead of pulling everything in, pushes everything out. This is the idea behind white holes, one of the most intriguing and speculative concepts in theoretical physics. Imagine a place where the rules of gravity are reversed, where instead of falling into a singularity, everything is expelled outwards in a constant stream. White holes are the theoretical mirror image of black holes, and if they exist, they could completely change our understanding of space and time. But are they real, or just a mathematical curiosity? White holes are predicted by Einstein's equations of general relativity, but they've never been observed. The idea is that a white hole is like a black hole in reverse. Instead of pulling matter in, a white hole pushes matter out, and nothing can enter its event horizon. In theory, a white hole could be connected to a black hole through a wormhole, creating a passage between different regions of space-time. This has led some physicists to speculate that white holes could be portals to other universes, or even a way for information lost in black holes to be preserved. However, there are several problems with the white hole theory. For one, white holes would be incredibly unstable. Any matter or radiation near a white hole would be expelled at such high speeds that it would likely disrupt the white hole's structure. Additionally, no evidence of white holes has been found, making them a purely theoretical concept for now. But some physicists believe that they could exist in the early universe or in regions of space where extreme conditions allow for their formation. Could white holes be the missing counterpart to black holes, or are they simply a theoretical curiosity? If they exist, they could provide answers to some of the most profound questions in physics, such as the fate of information in black holes and the possibility of travel through wormholes. But for now, white holes remain a tantalizing mystery waiting to be discovered. The universe is full of galaxies, stars, and planets, but not everywhere. There are regions of space so empty, so devoid of matter that they boggle the mind. One such region is the giant void, one of the largest known structures in the universe, measuring over 1 billion light-years across. But why is it so empty? Imagine a region of space so vast that it contains almost nothing. No galaxies, no stars, just an eerie emptiness stretching for billions of light-years. That's the reality of the giant void. A cosmic desert where even dark matter is scarce. But what caused this enormous void? And what does it tell us about the structure of the universe? Voids like the giant void are part of the large-scale structure of the universe, sitting between the filaments and clusters of galaxies that make up the cosmic web. These voids are thought to have formed early in the universe's history, as regions of space with lower densities of matter were stretched and expanded by the gravitational pull of surrounding galaxies. However, the giant void is so large that it challenges our understanding of how such structures form. One theory is that the giant void could be the result of cosmic inflation, a rapid expansion of space that occurred shortly after the Big Bang. During inflation, tiny quantum fluctuations in the density of matter could have been stretched across vast distances, creating regions of high and low density. Over time, the low-density regions would have expanded into voids, while the high-density regions collapsed into galaxies and clusters. Could the giant void be evidence of a larger structure in the universe that we haven't yet discovered? Some scientists speculate that voids like this could be connected to the multiverse, where regions of space with different physical laws exist beyond our observable universe. As we continue to map the large-scale structure of the cosmos, we may find answers that challenge our understanding of the very fabric of reality. When it comes to cosmic explosions, nothing compares to gamma-ray bursts, GRBS. These incredibly powerful events release more energy in a few seconds than the sun will emit over its entire lifetime. But what causes these immense bursts of energy, and what can they tell us about the most extreme conditions in the universe? Imagine witnessing an explosion so powerful that it outshines entire galaxies, lasting just a few seconds before fading away into the darkness. That's what happens when a gamma-ray burst occurs. These bursts are so rare and so powerful that they could devastate entire star systems, and yet we're still not entirely sure what causes them. There are two main types of gamma-ray bursts: long GRBs and short GRBs. Long GRBs are thought to be caused by the collapse of massive stars into black holes, known as hypernovae. As the star collapses, it releases jets of gamma rays that shoot out into space at nearly the speed of light. Short GRBs, on the other hand, are believed to be caused by the merger of neutron stars or black holes, creating a burst of energy that lasts only a fraction of a second. But GRBs aren't just spectacular, they're also dangerous. If a gamma-ray burst were to occur close enough to Earth, the radiation could strip away our atmosphere, causing mass extinction. Fortunately, most GRBs occur in distant galaxies, far from our solar system. However, the sheer power of these explosions raises questions about the nature of black holes, neutron stars, and the extreme conditions that produce such immense energy. Could gamma-ray bursts be the result of processes we don't yet understand? As we continue to study these powerful events, we may uncover new insights into the formation of black holes and the behavior of matter under extreme conditions. But for now, GRBs remain one of the most awe-inspiring and mysterious phenomena in the universe. The universe had a beginning, and one day it will have an end. But how will the universe meet its ultimate fate? Will it end in a big freeze where everything drifts apart in a cold, dark void? Or will it collapse back in on itself in a big crunch? And then there's the most dramatic possibility, the Big Rip, where the very fabric of space-time is torn apart. Each of these scenarios paints a different picture of the universe's final moments, but which one is correct? Imagine the universe billions of years from now. The stars have burned out, the galaxies have drifted apart, and all that remains is a cold, dark void. This is the Big Freeze, where the expansion of the universe continues forever until all energy is evenly distributed and no new stars or galaxies can form. But that's just one possible fate. The fate of the universe depends on the balance between dark energy, which is causing the universe to expand, and gravity, which is trying to pull everything back together. If dark energy continues to dominate, the universe could expand forever, leading to the Big Freeze. In this scenario, galaxies will drift apart, stars will burn out, and black holes will eventually evaporate, leaving behind a cold, empty universe. But if gravity overcomes dark energy, the universe could reverse its expansion and collapse back in on itself in a big crunch. In this scenario, galaxies, stars, and planets would be pulled closer together until everything is crushed into a singularity, similar to the one that existed before the Big Bang. Some physicists speculate that the Big Crunch could lead to a new Big Bang, creating a cyclic universe that expands and contracts indefinitely. Then there's the Big Rip, the most extreme and dramatic of all scenarios. If dark energy grows stronger over time, it could eventually tear apart galaxies, stars, planets, and even atoms. In this scenario, the universe would be ripped apart, leaving behind nothing but a sea of isolated particles. Which of these scenarios will come to pass? The answer lies in our understanding of dark energy, which remains one of the biggest mysteries in cosmology. As we continue to study the universe's expansion and the behavior of dark energy, we may one day be able to predict the ultimate fate of the cosmos. But until then, the end of the universe remains one of the greatest unanswered questions in all of science. As we've journeyed through these 25 space mysteries, one thing is clear: the universe is far stranger and more complex than we could ever have imagined. From the enigmatic nature of dark matter and dark energy to the possibility of alien civilizations and the ultimate fate of the universe, each mystery challenges our understanding of reality. But these mysteries aren't just puzzles to be solved. They're also a reminder of how much there is still to discover. With every new observation and every new theory, we take one step closer to unlocking the secrets of the cosmos. But for every question we answer, new ones arise, keeping the mystery alive. What do you think? Could the answers to these mysteries be within our reach? Or will some questions remain forever unanswered? Let us know your thoughts in the comments below. And don't forget to subscribe to Mystery Beyond Reason for more deep dives into the most fascinating and mind-blowing mysteries of the universe. Until next time, keep looking up, because the universe always has more secrets to reveal.